my pleasure to welcome you to today's ECT Star introductory colloquium on the science topics of the workshop Machine Learning for High Energy Physics on and after Lattice. This workshop was planned for 2020 but has been deferred to 2021 because of the COVID-19 pandemic. It will focus on machine learning and artificial intelligence that has seen enormous progress in the last few years, much in the form of deep learning. There have been dramatic improvements in performance on several challenging problems, many of them directly related to physics. In fact, many of the techniques have had their origins in physics anyway. As you know, the intention of this colloquium series is to introduce and publicize the science case of the workshop to a wider audience. Today's talk will be given by Cranmer, who is Professor of Physics and Data Science at New York University and Executive Director of the Moore Sloan Data Science Environment of NYU. His background is in experimental particle physics, and he works on the Atlas experiments at the LHC. Professor Cranmer obtained his PhD in physics from the University of Wisconsin-Madison in 2005. He was awarded the Presidential Early Career Award for Science and Engineering in 2007 and the National Science Foundation's Career Award in 2009. Professor Cranmer developed a framework which enables collaborative statistical modeling, which has been used extensively in the discovery of the Higgs boson in July 2012. Interests are at the intersection of physics, statistics, and machine learning. Kyle, thank you for agreeing to give this talk.
Okay, thank you very much for having me. It's my pleasure to speak. I'm going to be talking about machine learning for high energy physics on and off the lattice. So to get started, I'll just give a preface that I was asked to give a colloquium to ECT Star to introduce a workshop that we're going to be having in September of 2021 called Machine Learning for High Energy Physics on and off the Lattice, since the title of the talk. And the audience that I have in mind is are the sort of the theoretical physicists of ECT Star, some of which I'm imagining might actually be experts of machine learning in some areas. Some I'm imagining are aware broadly of what's going on with machine learning, but aren't experts and might be either curious or even skeptical of what's going on there. And some of the audience that's really just not following these developments at all, and so I'm going to try to hit on some topics that will hopefully be accessible for all these different components of the audience. So first, a word about myself. So most of my career has focused on Higgs physics. Actually, I'm nominally an experimental particle physicist working on the Atlas experiment. So I worked for searches for new particles and various things like that. Early on, many years ago, I played around with machine learning a little bit in the 90s and the 2000s. But then I really shift my focus primarily to work on classical statistical methods for the Large Hadron Collider in preparation for all the data that we were going to be having, and taking into account that there are a lot of uncertainties when we're dealing with data, especially at a hadron collider like the LHC. That all evolved over the next decade or so, and of course in 2012 we discovered the Higgs, which was fantastic. The next year I had a sabbatical, which was very nice, and that was also right around the time that deep learning started to emerge. So I took some time during that sabbatical to think about how deep learning and sort of the way that we traditionally go about doing physics are related, and how we can take advantage of deep learning, and what's different about it, and etc. And in the last few years, I've been thinking about machine learning for the physical sciences kind of more generally. In terms of my own work, I'm still active in work at the Large Hadron Collider, but I've been branching out. Have some papers working on dark matter astrophysics, dynamical systems, quantum systems, and recently lattice field theory. So during that time, I've amassed sort of a large group of collaborators, which have been a lot of fun. This is just some subset of those collaborators. Some of them are computer scientists, some are applied mathematicians, some are physicists of different types, and it's just been a lot of fun, and I've learned a lot, and I've really enjoyed sort of this theme recently. So I'm going to take you back to 2012. That was in July 2012 is when we announced the discovery of the Higgs boson. I'm sure you're familiar with that. And the analysis of the data here was sort of a very classical statistical analysis of doing a sort of maximum likelihood fit, and then trying to characterize our uncertainties to be able to do some sort of hypothesis test. And that hypothesis test, you can also think of in some sense as an example of a classification task. You're trying to ask, in one hypothesis, there's no signal present, and in the other hypothesis, there is a signal present, and you're just trying to choose between those two situations, and you're trying to classify based on the data which situation you're in. You can also think of these fits as sort of examples of density estimation, where you're trying to understand what the distribution of the data looks like. And so anyways, these were all very kind of classical things. Interestingly, the same month that we announced the discovery of the Higgs was one of these milestones in deep learning, a paper that included Geoffrey Hinton that was using deep neural networks, really for the first time that deep so-called convolutional neural networks, which are well suited for image tasks, started to do much better than any other kind of model that was around before for this image classification task. And in really just a few years, the pace was and continues to be incredible. It went from basically having new state-of-the-art results using this idea of deep learning to in 2015 having systems that were better at classifying images than humans. That seems like a funny statement. How could you be better than humans since humans are giving the labels in the first place? And that basically is just that humans don't always agree. They make some sort of mistakes when labeling the images. And so at this point, the neural networks are basically learning, in addition to how to classify, how to like predict, what kind of mistakes people are going to be making. So, this was really tremendous progress, and it's interesting. But as a physicist, it's pretty easy to, not take this very seriously because everything seems like pictures of cats and dogs, and that seems very different from like first principles physics that we're often very interested in. And so what I'm going to try to do is sort of bridge the gap or close the gap between what seems like a very ad hoc kind of unprincipled cat and dog classification task to something very principled like lattice field theory, and try to show how all of this is very related and how these kinds of developments are actually very relevant for physics. So when we use the term deep learning, part of that is referring to this change in perspective, or at least change in approach that has happened recently. So if you asked about an image classification task, here's, and many of the examples in early deep learning were image based. So, and this is a slide taken from Jan LeCun, my colleague at NYU, who's well known for introducing the idea of these convolutional neural networks and a champion of deep learning. So his point here is that traditional classification or pattern recognition would take an image like this, which is very complicated data. The dimensionality of this data is the number of pixels times sort of the number of colors. So there may be hundreds of thousands or millions of the data point is like a million dimensional vector to describe this image. And most machine learning techniques didn't work very well with such high dimensional data. So what you would usually need to do is extract some features from this image. Like, so someone would write an algorithm that might try to search for, like, edges and circles and wheels and things like that. And then after extracting certain kinds of features, you would train a relatively simple classifier to try to tell the difference of, is this a car or a bus or a cat or something like that. And then as things evolved, it went from entirely sort of hand engineered features to situations where there might be some mid-level features that kind of that might actually be learned, and they might actually be learned in an unsupervised way. And so we'll talk more about the difference between supervised and unsupervised, but basically unsupervised happens when you provide a lot of data examples without necessarily giving them labels, like this is a cat or this is a dog or a car or something like that. And so what you can do, for instance, is try to figure out ways to compress this image into some lower dimensional representation, and then that lower dimensional representation might be given to a classifier. So that was what was happening sort of right before the rise of deep learning. And what's happened with deep learning is a more end-to-end style where you have a trainable classifier, and before that you have a series of sort of feature extraction algorithms, low-level features, mid-level features, high-level features. But instead of these being fixed ahead of time, they're all learned jointly. So you're in an end-to-end fashion, you're figuring out how to extract low-level features, mid-level features, high-level features, and then the final classification decision. And so just to give a little bit of a visual example, when in these image classification tasks where you're working with images, it's common to use a type of neural network, this convolutional neural network, which basically takes little filters and slides those filters over the image. And so you can think of them as like looking for, like a little edge detector filter or something like that. So this little filter you can see is looking for edges that are oriented in different directions. And by sliding this filter over the image as in the form of a convolution, you're basically, the feature detectors are looking for these, these edges and things like that. So this was the very low level features. And then they can be composed into mid-level features. So here you're starting to see some weird shapes emerge and things like that. And then finally, high-level features, you're already starting to see things like recognizably an image of a bird. I don't know what that is, a wheel maybe. This definitely looks like a wheel. So all sorts of different, so these turn into filters that you're scanning over the image to try to detect these kinds of things. And then depending on how much these filters respond, then the trainable classifier has a pretty easy job of, or relatively easy job of trying to classify. But importantly, all of these filters are learned jointly. So that was kind of the initial narrative, at least around what's going on with deep learning and why you might expect it to be powerful. In the meantime, instead of just classification, you've seen deep learning evolve into, instead of just saying that this is a cat, being able to say, the cat is in this box, to being able to work with an image that might have many objects in it, like cats and dogs and rubber duckies, to being able to actually outline the images in what's called an image segmentation task. So that's pretty interesting. And you could see how that would be useful in a lot of practical applications. Then it's evolved even more in computer vision to where you can not only outline objects, you can sort of label what type of object they are. So this is called, so this is the segmentation where you see people and cars. Then there's a version where you can actually label different instances. So you have like different instances of people and cars and things. And then this one I think is really cool, is just from these individual images, you can try to predict how far away that object is. And you might think, well, that's impossible from an image, right? Like you don't have parallax, you don't have two eyes, you just have one image. So how could you possibly know how far away these things are, the stop sign or the people? But if you look at this image, you know that this stop sign, this stoplight is farther away than this car, right? And how do you know that? Well, partially experience, but more specifically, it's because you know roughly how large cars are, and how large stoplights are and how large bicycles are. So you can infer how far away things are through statistical properties things that you've seen in the world. So, so machine learning is able to extract this kind of statistical regularities and infer things like how far away the car is, even though it's not done geometrically in terms of something like parallax. In addition to images, there's been really interesting work in the area of natural language processing. And so these are some really interesting examples where, for instance, you take a large body of text, and now the text is not so obviously represented as a vector in some an RN or something like an image. You can think of the pixel values as each pixel is a different direction, and the pixel value is like the coordinate along that direction. When you work with just a bunch of words, you don't have any natural representation. So one of the things that's happened in deep learning is figuring out different techniques for taking complicated structured data and then figuring out how to represent it in essentially as a vector in RN. So in these examples, you see taking a lot of words and through an unsupervised learning procedure, being able to embed those words in this vector space. And what's interesting is that the vector space ends up encoding some semantics. So if you look at the vector that goes from king to queen and the vector that goes from man to woman, you see that those vectors are actually aligned, which seems to indicate some sort of semantics around gender. And then here you see the vector between walking and walked and swimming and swam. Again, is capturing some semantics around tense. And then similarly, if you look at the vectors between a bunch of countries and their capitals, you also see that they're basically aligned. So, so the fact that this is happening is pretty impressive. And since then, there's been a lot of work to actually solve tasks like machine translation, where you take a sentence, say in English, and you translate it into German or French. And originally this was done in a supervised way where you had to have a bunch of text that was actually translated. But now there's been quite a bit of success in just taking a bunch of language in one, a bunch of text in one language, a bunch of text in another language, and the systems are able to basically align the texts and figure out how to translate them, which is seems like science fiction, but is definitely happening and powering what happens on Google Translate and things like that these days. The other kind of thing that's happening that's getting more relevant for what I'll be talking about later is what's called generative modeling. So here are one of the early examples where the training here is a bunch of images, say of birds and ants and monasteries and volcanoes. And after showing a bunch of examples, these systems essentially try to learn what the probability distribution of these images look like. And then they can sample from that probability distribution and get new examples. So these are new examples of volcanoes that are not real pictures of volcanoes. They're drawn from what this neural network is approximating as the distribution of images of volcanoes. And so these look pretty impressive. And so again, remember that these are sampling from a very, very high dimensional distribution in the space of images. If you look at the monasteries, they look, they're recognizable. They don't look great. The ants look pretty good, but kind of distorted. The birds look recognizable, but their aspect ratio and proportionality is very off. So this I feel like is sort of like when you look at the drawings of your young children, they're sort of recognizable, but the proportions are all off. So this is sort of the state of deep learning as a 3-year-old or something doing drawings, and now deep learning has matured quite a bit, and the results look like this. So these are trained essentially in the same way that I just described, and they are examples of images of people that don't really exist. They're samples from the probability distribution of faces of celebrities as modeled by a neural network, and these are very high dimensional. I don't know, roughly 1,000 by 1,000 pixel images. So it's like a 3 million dimensional space. And they're very high resolution. If you look at they're high fidelity, I should say, if you look at like the hair on this person's face or her eyes and things like that. So, so this is, this is pretty impressive. And, we have not had capabilities like this in the past. And so the question is, how can we leverage these kinds of capabilities, for science, right? Here's another example, which is an audio example. So instead of a picture of a face, it's going to try to generate some audio, and I'll let you listen to it. And what's also interesting here is that the input to this neural network is actually the text that you would like the neural network to read. So that it's like a conditional distribution. Given the text, what's the probability distribution over waveforms? And the waveform you can think of as basically the amplitude of this wave at every time step, and it's sampled at kilohertz level for more than a second. So this is some 100,000 dimensional data point that's being drawn from this distribution. So now you can listen to it.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and large stone.
So that sounds pretty incredible. I'll play one more time.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone. Okay,
so hopefully that came through on the recording, but it really sounds, very, believable. And this is again the type of model that instead of modeling voices, you might imagine trying to model some sort of time series data that happens in physics. The other, big advancement that made a splash, a couple of years ago was the use of reinforcement learning to try to play games like chess. And then after chess, playing a game called Go, which is considered to be, significantly harder, and was really, a milestone in artificial intelligence, was to be able to beat, well, even achieve human level performance, much less beat the best player in the world. And the newest versions of this, instead of being trained by looking at lots of historic games, it actually learns just by playing itself over and over, and ends up learning some, at first strategies that are recognizable by humans, and later strategies that are less recognizable by humans. So this was really very exciting. And now most recently, this week, there were announcements of using techniques. Again, this is a work from DeepMind, to try to estimate how a protein would fold by looking at the sequence of amino acids. And so this is one of these grand challenges in, in biology and physical chemistry, to try to do, solve protein folding, which has enormous, impact on society. And you see this competition that's been going on since 2006, every 2 years, the CAS competition. And this is a metric that they use called GDT, which is essentially saying, what fraction of the when you try to place the location of the atoms and your or the amino acid in your protein, like how many are close enough to where you think they should be based on experimental data. And so you can see that it wasn't working very well for many years. And then the last, well, in 2018, there was a pretty big improvement using deep learning. And then this last year, what was just announced, was hitting this milestone of a score of 90 for GDT, which is basically when these kinds of predictions are at the same level of fidelity roughly as the experimental measurements. So this means this was really like kind of a, it was really a big milestone for protein folding that was just announced. So with all of this in mind, we have organized a conference focusing on machine learning for the physical sciences. We're having the third one this next weekend at the NeurIPS workshop, which is the largest machine learning conference in the world. You see our organizers, so physicists of various stripes and machine learning researchers. Of course, this isn't the only one of these conferences. There's been a number of conferences, oftentimes more topical, going on around the world in the last few years. And the workshop that we're going to be hosting at ECT Star in September 2021 is one such workshop. And the focus here is really on high energy physics, largely on the theoretical end, with an emphasis on the lattice, but not only on the lattice. And so you see the types of topics that are discussed here, including applications to a renormalization group, the gauge gravity correspondence, and things like that. And I'll hit on some of these topics later on in the talk. Okay. I'd also like to sort of advertise review article that we wrote last year, which was nice to see featured on the cover of the Review of Modern Physics. You see the authors here, and this was a fairly comprehensive picture of machine learning in the physical sciences. And I'll just go quickly through the table of contents so you get a feel of what kind of information's in there. So there's a basic introduction about core concepts from machine learning, and then there's a section on statistical physics. And actually, a lot of that is focused not so much on using machine learning for solving problems in statistical physics. It's largely about using statistical physics to understand the theory of deep learning. And this is really fascinating work, and I admire it, but I'm not really going to spend time on that in this talk, but I will just point to a little bit at the very end. But I will talk about some applications of machine learning in statistical physics, for instance, identifying phase changes and things like that. Then there's a section on particle physics and cosmology, and I will say a little bit about the use of machine learning for inverse problems in this context, but not much else in this talk. Then there's the use of machine learning for many-body quantum matter, which I'll say a little bit about, and there's uses in the connection to quantum computing, which I won't say very much about. And then there's uses in chemistry and materials, and I'll only make some reference to that. And then there's the idea of sort of accelerating AI, which I won't refer to in this talk. But you see that there's a lot of different applications. If any of these are interesting to you, I invite you to check out that review. Okay, so since one of the challenges in this talk is really figuring out how to manage such a broad array of different topics, I'm just going to start with kind of an informal taxonomy of different things to consider when trying to kind of navigate this enormous body of literature. So the first thing I think that makes sense to ask is, what is the task that you're trying to solve, right? And usually that, if it's a task in physics, it might take some translation to figure out what term in machine learning you would use that's the kind of corresponding idea. But the the titles in machine learning, typically along the lines of things like dimensionality reduction, where you might have complicated data and you want to summarize it, find the relevant features. Things like an order parameter might be an example of something like that. There's clustering, where you might say, here's a bunch of data, can you cluster it into groups? I don't necessarily know how many groups there are. So that could be something like trying to identify different phases of matter. You might say, here are examples of configurations of some system. Is there evidence that they should be clustered into different phases? And if so, how many are there? Then there are tasks like density estimation, where you're trying to understand a distribution you're trying to estimate some sort of distribution. And that distribution, for instance, happens a lot when you're talking about statistical physics or thermodynamics and things like this, and also happens in the context of like lattice field theory. Then there are various classification tasks, which you can think of as similar to the clustering problem, but here you're usually saying that you have examples that are labeled. So you can say, like, here are examples of cats and dogs, or here's examples of something in a one phase and another phase, or in particle physics, experimental particle physics, you might try to classify a collision to say, do you think this is a Higgs boson collision or a background collision? Then there are regression tasks, where you're trying to understand some sort of input-output relationship, like which is essentially like a curve fitting problem. But sometimes that curve fitting problem is a very complicated curve fitting problem. And then there are other tasks which are not usually don't necessarily have a name in machine learning, but definitely happen in the physics context, where you just have an optimization objective and you want to optimize it. And so most machine learning these days is cast as an optimization problem, and so the objective that you're trying to optimize, it corresponds to what this task is. And so sometimes, for instance, say we want to find the ground state energy of some system, and we have a variational model and ansatz for what the system's ground state might look like. Then we just want to minimize, say, the energy of that system to try to approximate the ground state energy. So that's just a straight optimization problem, and where you can use machine learning tools, but it's not necessarily one of these tasks. The next part of the taxonomy, I would say, is basically what is the learning paradigm. So you have supervised learning, where the training involves giving a bunch of essentially input-output pairs, like an example and a label, which is like, here's an example image and I'm telling you this is a cat, or here's an example image and I'm telling you that it's in this phase or another phase. Or for a regression task, you could say, here's an example and I want you to, estimate the mass of a particle or the parameter of a Hamiltonian or something like that. Then there is unsupervised learning, where you just provide a bunch of example data. You don't have any labels associated to it. And that seems maybe like, well, what could you do? But and there are many examples, for instance, in clustering and density estimation, that fit in this unsupervised learning paradigm. If you're trying to understand a probability distribution, you just have a bunch of examples. You don't need to give them labels. And if you see an overdensity in one area, then the density should be large, and an underdensity in another area, then the density should be small. And then there's what's called reinforcement learning, which is like what was used for the playing Go, where you're trying to optimize some sort of reward, and you might not get and you usually have something like an agent that is taking actions, and you're trying to learn a policy for that agent. What action should it take to be able to optimize some sort of long-term reward? That happens occasionally in physics context, but it's a little bit less. Sometimes you see it when you think about things like experimental design, or for instance, if you're trying to do something like quantum tomography or something, you sometimes see uses of reinforcement learning. Now, the next part of the taxonomy that I think is useful is to think about what is known for the data distribution. When you talk about machine learning, it's all about data, right? So what is the data? What's the source of the data? So when you think about, for instance, images of cats and dogs, you don't know what the distribution is. You just have a bunch of examples. So people say that the distribution of images for cats and dogs is an implicit distribution. You don't have access to the distribution. You only have access to data samples. And there are other examples that happen in physics that fall in that category, and I'll give an example shortly. Then sometimes we have something about we know something about the data distribution. So it might be tractable, but up to some unknown normalization constant. So for instance, if you're thinking about a Boltzmann distribution, where the Hamiltonian, or the action, you can assign some sort of some weight associated to a state or a configuration, but you don't know how to normalize it properly, because the partition function might involve an intractable integral over all possible states, but you do have some information. And then the best case scenario is if you actually have a tractable probability density in the first place, in which case you might ask, why are you even using machine learning? But maybe it's just because you want to approximate this to make it faster, or some other practical concern. Okay, and the last stage of the taxonomy, which is from a kind of physics perspective, is thinking about, I would say that roughly there are a few different types of physics where the use of machine learning just looks very different. So you have basically purely theoretical or computational physics, where there is no, you're not doing experiments, so you don't have some apparatus that you need to understand. You don't have noisy measurements or noisy observations. And so what you often have access to is, it's fully observed. So you get to see the full state, even if that might be like a quantum state that's not actually observable in a real experiment. So you have access to everything, and oftentimes you also have access to this unnormalized probability, like the Boltzmann factor for the the action or the energy. And this kind of thing comes up in lattice field theory and statistical physics and quantum many body physics quite a bit. The next sort of broad class of physics problems, I'd say, are ones where you have some sort of simulation for what's going on. You have a theory, you have a simulator. It might be a very accurate simulator, but it's trying to describe experimental data. So And so, and the experiment has a, a noisy, noisy apparatus involved. And so you need to model that noise. And in those situations, because you usually have many observables, or sorry, many random variables that you don't get to observe. Those are referred to as latent variables. And so you have, integrals that you're confronted with. And so usually in the situation, the probability distribution is totally intractable. But you can generate synthetic data. So it's an implicit distribution that that's not like actual pictures of, say, cats and dogs or actual data. It's simulated data, but you do not have a tractable probability density for the data examples that you're generating. And then the last class is really purely observational work. So think of like astrophysics or something like that, where you don't necessarily have a very good theoretical model describing what's going on either. You just have a lot of data and you would like to do something with it. And of course, there's a lot of interesting work going on here, but it's sort of sufficiently different from the other examples that I'm not going to talk about this case in this talk. But I'll touch briefly on this and then spend the rest of the talk talking about these more kind of theoretical problems. So, so this is where a lot of the work that I do personally is thinking about a situation that's relating how theorists and experimentalists interact with each other, and that part of the scientific workflow. So I'm imagining on the left side essentially is theory, where I have some parameters of my theory, which might be, for instance, the mass of the Higgs boson and how it interacts with other particles. So like they might be constants inside of the Lagrangian of some physical theory. I might also have some nuisance parameters which describe things like in my detector, like calibration constants of my detector that I don't know perfectly. And once I specify, how my detector should respond and what the parameters of my theory are, then what I have in my simulation is the ability to predict what the distribution for the observed data should look like. And so, this predictive direction is sometimes referred to as forward modeling or generative, like this is a generative model for the data or just simulation. And inside of that simulator, there are often many other random variables that happen that involve, for instance, how particles decay or how they ionize inside of the detector or something like that, which I don't get to observe as an experimentalist. I only observe X. So these other random variables that I don't get to observe are what are referred to as latent variables, Z. And then from that complicated data, I may try to summarize to some summary statistics. So for instance, from the complicated data at the LHC, I might try to summarize into an estimate of like the mass of a particle. That would be an example summary statistic for like a particular collision. And then based on a lot of this data, then what I would like to do is turn the whole thing around and solve this inverse problem where based on the data, I can say, what's the probability of these parameters of interest or some kind of inference problem about the parameters of the theory given the observed data. So this inverse problem is typically very, very hard if the predictive model is like a simulator. And so so I'll give an example there. So here is a real data example, right? Which maybe you've seen something like this. Sorry about the sound there. So you see the balls bouncing through this bean machine or Plinko machine or Galton board, whatever you want to call it. And so that as the balls bounce left and right, it's very common to model something like this with either with a Gaussian distribution or more specifically, you can think of it as a binomial distribution because you're either bouncing to the right or to the left on each step. And so this is what you would maybe expect the distribution to be, where theta is the bias of, say, the chance that the ball bounces to the right. So theta equals 1/2 would be the natural situation here. Now you actually take this distribution and you predict the width of this curve. It's actually a lot narrower than what you observe, which is something that I learned painfully right before giving a lecture to my undergraduates. And when I was trying to figure out what was going on, I took a slow motion video of this. And so here we go. If you actually watch a video of what's happening, you see that it's a lot more complicated. These balls are bouncing all over the place. And it's not at all like a simple go left, right, binomial distribution. And so I have no idea what this distribution looks like down at the bottom. There's also some interplay between the pitch of these pins with the pitch of the bins, which doesn't match up well. So I can't write down an equation for what this distribution looks like, but I can simulate it, right? So I can, the fact that I can simulate it is interesting, and then the simulation can have some parameters in it, which are, for instance, the size of these balls, how bouncy they are, the separation between the pins, various things like that. And so in principle, the distribution, if X is is telling you which bin do you land in at the bottom, the distribution P of X given theta, which are the parameters of the simulation, is given by an integral over the latent state Z, where you're marginalizing out or integrating over all the possible paths that a ball might take to end in one of these bins. So that's symbolically what the right answer is, but you can't really do this integral practically, because you'd have to sum over all possible paths through the simulation, and that typically grows combinatorially or something like that. So you have this this integral is typically intractable, and that's the reason why this distribution is intractable, or you say like an implicit distribution. So this motivates like a whole new class of inference algorithms that don't involve knowing this likelihood function, but instead just rely on being able to generate samples from the simulator in the forward mode. And it's not surprising that if you're working with a bunch of simulated data, that this is going to be maybe a very good use case for machine learning. And since you know what parameters you use to generate the data, you can even use supervised learning techniques and things like that, which is where a lot of the real success in machine learning has happened. And so this idea, is very general. It's certainly relevant for particle physics, but really science is, replete with very high fidelity simulators that go from particle physics to neuroscience to the spread of epidemics, imaging of black holes, gravitational lensing, the evolution of the universe, protein folding, molecular dynamics, fluid dynamics, etc. And so what I think is really exciting about this area is there's just a profound shift that is happening, because there are so many areas where we have these high fidelity models, but until now we have not been able to use them directly for doing inference because of this intractable inverse problem. But the developments in machine learning are giving us basically effectively a bridge that's able to relate the microscopic physics that's going on in the simulator with the macroscopic emergent phenomena that we are observing, and to be able to connect that emergent phenomena back to the parameters of the microscopic model. And so if you can make that connection, that's like incredibly powerful. And I find it's like a very compelling step in the in the evolution of science. So there have been various workshops. Here's one in 2017 at the International Conference for Machine Learning that's specifically on this issue of what to do with these implicit models, where you can you can generate data, but you don't have a tractable likelihood function. And so they're making this point that many phenomena are described by simulators like this. And for instance, they're used in particle physics to generate collisions at the LHC. And there's a lot of very hot topics in machine learning that are relevant. And so, for instance, the generative adversarial network that made the pictures of those faces that I showed you earlier, techniques related to variational inference, which is very closely related to the variational free energy paradigm that's used in statistical physics a lot, something called approximate Bayesian computation, and then issues related to what's called two sample testing. This is basically hypothesis testing. And so there's just a huge nexus of really interrelated techniques and developments that are happening. And so this area is just exploding right now. So in the context of particle physics, I'll just go through this one quickly, is that I have a generative model. At the very beginning, I say start off with the Lagrangian of the standard model. I can use Feynman diagrams to try to predict what the distribution of the energy and momenta of the particles of a certain scattering process would look like. But this is what you can do with a pencil and paper, but this is not the end of the story. We also, if you're producing, for instance, quarks and gluons, they radiate. And they radiate, those gluons radiate more gluons, and et cetera. So, and then there's another process called hadronization. And then finally, these dark green particles are actual stable particles that are flying into my detector. And then I need to model the interaction of these particles with my detector. And so you can think of the detector interaction, it's also stochastic for the same incoming particle energies and momenta. The response of the detector is random. It could be, you have fluctuations in the detector response. And so we can simulate that with Monte Carlo techniques. And while we can generate fake data, we do not have a tractable likelihood function. That would mean something like the likelihood for some observation X, given the parameters of this theory and of the detector simulation, would involve calculating this enormous integral over all of these things that happen. And that's, for one collision at the LHC is sort of 100 million dimensional integral. So that's not going to happen anytime soon. So here's where machine learning is being used in this context, is that we can use the parameters of the simulator. We can run the simulator for some synthetic data and feed the synthetic data and the parameters into a neural network. And so instead of taking the synthetic data and trying to predict the parameter values, the neural network actually takes the data and the parameter value as input, and the output is an estimate of the likelihood function or a likelihood ratio. And once you have this likelihood ratio, then you can do inference by scanning through the parameters theta as if you had a tractable likelihood model. So this is being used and has given rise to, hasn't been used yet for like actual measurements. This is, very new, but the studies that have been done point to this providing like a very significant improvement in sensitivity for studying, for instance, effective field theory at the Large Hadron Collider. So that would be like looking for deviations from the standard model at the Large Hadron Collider, which is one of the flagship topics for us to study right now. I also point out that this is very relevant, for instance, in the context of nuclear physics, if you wanted to try to extract generalized parton distribution functions, say at the electron-ion collider or some other experimental facility for nuclear physics. So part of how this works, I'll just give a brief idea, is that we can simulate data, for instance, for two different values of this parameter point. And if I want a likelihood ratio, what I want to know is compare the likelihood for one value of the parameter point, say like over here in this plot, compared to another point, which might be, say, the center of this plot. Like I'd like to evaluate the ratio of the likelihoods of those two spots. So I can go to those two spots and generate synthetic data, and then I can train a classifier to try to tell the difference between them. And so typically when you're doing binary classification, you might use a loss function, which I'm writing out symbolically as this. So it's really, I should say, a functional, right? So it's a scalar valued functional of the function S. And so here's just a simple 2D example. Let's say I have a bunch of examples that are red dots and blue dots. And you can think of the blue dots as signal and the red dots as background, if you will. And you're trying to, so these might be, for instance, it's like examples of cats and dogs, right? And so I'm trying to classify them. And so if I could come up with a function where, X is the location in this two-dimensional space, where, if I could come up with a function S of X, such that when I evaluate the function, it gives me 1 if it's from a blue dot and 0 if it's from a red dot, then I've solved the problem, right? That's just one way of casting the problem. And so because these distributions overlap, there's no way that I'm going to find a function S that does that perfectly. So I need to figure out some way to trade off the different kinds of mistakes that S might be making. So here's one such way that seems at this point very ad hoc, is let's say the data comes from the distribution H naught, which are, say, the red points, then I want S to give me 0. And if it gives me anything other than 0, that's a penalty. And I'm going to do it as a squared penalty. And then if the data comes from H1, the blue dots, I would like S to give me output 1. So anything different than 1 is a penalty. And again, I square it. You could say, why square it? Why not cube it or to the 4th power? And you're right. But let's just work with this for a second. So this is a functional, and I've written it out symbolically, even though I don't actually know the distribution. These are implicit distributions. So I can't really do this integral, but I can write it down. So if I use calculus of variations here to find the function S that minimizes this loss, I find this function. This is called the regression function. Anyways, this function S turns out to be 1-to-1 with the likelihood ratio. And there's a classical result in statistics called the Nyman-Pearson lemma that says that this likelihood ratio is the optimal way to try to solve this binary classification problem in terms of things like type 1 and type 2 error. So this is just a way of kind of a, a roundabout way of getting to this answer. But remember, I can't evaluate this likelihood ratio. So if I can approximate a function, if I can find a function that approximates this likelihood ratio, that's great. And so if I go back to here, the problem is, this loss functional involves these distributions that I don't know, but I can approximate this loss functional through samples. So if I have an equal number of samples from red dots and blue dots, then I can replace these integrals with their Monte Carlo approximations, where I just evaluate the integrand, and y here is either the label 0 or 1. So now I can actually approximate this loss functional. And now the question is, how do I find the function s that minimizes this? So I'm not going to search through the space of all possible functions. Instead, I'm going to use a variational approach and think about some very highly flexible family of functions. And that's where neural networks come in. Neural networks are just known to be a very, very flexible class of functions. There's a few universal approximation theorems and things like that, but it doesn't really matter. It's basically just a very flexible set of functions, and they have some parameters, which are called phi here. And so then if I just minimize this function with respect to the parameters phi, I can try to, I can try to approximate this the system. So in this way of thinking about it, I think of machine learning. This shouldn't say NN. This should say machine learning as. That machine learning is basically applied calculus of variations, and the neural network is playing the role of a very highly flexible family of functions. And so in addition to just being a highly flexible family of functions, you also have optimization algorithms that are effective for these non-convex optimization problems, even when you have millions or billions of parameters, which is incredible. And the idea here of deep learning is basically just the fact that the networks are, for instance, starting to have more and more layers, or now there are many more. This is not really the modern picture of deep learning anymore. Deep learning is now more a composition of various types of neural network modules that can do different kinds of things. And there's really a zoo of different types of neural network modules out there now. So this whole picture that I'm telling you about the inverse problems and simulation-based inference, we wrote a review recently on this topic, and I point you to that review. Okay. Now I'd like to switch to some topics in theoretical physics. It took a little bit longer than I anticipated on that first part. So bear with me as I get through some topics in theoretical physics. So one of the first areas that I'll talk about is the use of unsupervised learning for trying to find phase transitions. And so here's just a collection of papers that you might be interested in looking at. Some of these are kind of predated they didn't necessarily predate the rise of deep learning, but they're not using the deep learning so much. So some of these unsupervised learning tasks are really classical approaches. For instance, principal component analysis, where you have a bunch of data points and you're trying to find essentially two orthogonal directions that explain the variance. And so it's like an eigenvalue problem for the covariance. And you're basically saying this direction captures most of the variability in the data. There's a variation called independent component analysis, which is really not necessarily trying to find orthogonal directions, but just different independent components. And these kinds of techniques have been used, for instance, by looking at, in statistical physics, by looking at many configurations, say from an Ising model. And so here what you see, this is an Ising model where there's a conserved order parameter, which means that it's a little bit harder. You can't just look at say the magnetization of the system to try to cluster. And the data is basically just many examples of the spin states of this model, and by doing principal component analysis, you start seeing that there are a few directions that capture most of the variability of the data, and you can then combine these things into essentially something like an order parameter and find different phases. There's also been some work using classifiers, like machine learning classifiers, to solve the problem. This is, it's not exactly unsupervised learning because you do still assume that you have examples from two different phases. So you're imagining that you have like some parameter and some range, and so that the two endpoints are in two different phases, but you don't know where the phase transition happens. So, and so the goal here is basically to identify where is the phase transition. And so by training a classifier on those two different phases, you can essentially scan through the value C. And in this paper, the way that it's set up, as you scan through the value C, at first, the classifier is going to do well because you're basically saying everything is in one phase. And then the classifier will be confused for a little bit. And then when you're sitting at the phase transition and you basically divide the data according to this value C that you're scanning through, then the classifier again does very well. And then it gets confused again. And then if you go all the way to the point where you say everything is in the other phase, it's going to do perfectly again. I think there's different ways you can frame this problem, but this is the way that these authors framed it. And so this middle point of the W is the phase transition. And so they applied it, for instance, to a random field Heisenberg chain, which exhibits many body localization phenomena. And they were able to find the critical point where the phase change happens, and that agreed with some other studies that have been done on that system. There's also been a fair amount of work of using supervised learning for phase transitions. So some of the early work here, a neural network was used to try to classify two different phases, but here the training data is generated by using kind of traditional Markov chain Monte Carlo on, say, a ferromagnetic Ising model. But for every value of, say, the temperature that you're using, that you're scanning through, you're basically saying that you know what phase it's in because we've already studied the Ising model. So the point here was more like just understand how well can neural networks do at this problem. And so once you've trained the neural network, then you can ask how good is it at classifying the different phases. And you see that as you scan through the temperature, the prediction that it's in one phase or the other, quickly changes. And the classification performance is basically 100%, except for right near the critical temperature where it can be confused a little bit. So, so this was interesting work. The same approaches were used for something like a square Ising model. At first, the neural networks were fairly simple, kinds of feed-forward neural networks. This was a system where there was no conventional order parameter, so it's not just like learning something simple. It needs to learn something more complicated about the patterns here. Again, this neural network was doing very well at being able to identify the ground state or a high temperature state for the square ice system. And then they studied a system which they call the Ising lattice gauge theory, which the Hamiltonian's written here, where you have basically spins on the links, and you see different types of phase changes and phenomena that are happening here. And in this case, the simple neural network actually was not up to the task and was not successful in being able to identify which phase. And so they then moved on to using a sort of more advanced neural network like a convolutional neural network. And at that point, the convolutional neural network was very successful. And so the question is, what's going on? And so when they dug in a little bit deeper, they found that the filters of the convolutional neural network were essentially learning some local features that were going on. And they were able to show that it was actually very connected to Kitaev's toric code, which is kind of interesting. So here the convolutional filters are basically paying attention to some local physics to be able to do the classification task. There's been some very recent work by Gary Xu and company, which instead of trying to put the effort or the work on the neural network to solve things, they actually use a very simple type of classifier. And instead, kind of against the grain of like the deep learning thread, they go back into feature engineering. But the feature engineering is now based on these ideas of what's called topological data analysis, which is sort of very, I'm not going to go through the details of how this works, but it seems very natural that you're looking for basically persistence of certain topological features across scales. So you have these basically various approaches that you analyze the data, and from the raw lattice data, you're able to fill some features, and for instance, this two-dimensional plane, which then gets represented essentially as an image. And then this image is then input to a simple logistic regression classifier. And you see that the system, just by being trained on examples that are, deeply in one phase or deeply in the other phase is able to identify the phase transition. And so that's pretty cool, and also points to the fact that we can still keep thinking as physicists, and we can keep thinking about how to engineer features, and that's not against the rules, and we can improve things quite a bit by doing so. So this idea and this theme of like, okay, well, we can use the power of deep learning, but we don't have to give up on being physicists and having insight to our problems, is one of the areas that I'm very interested in. Is, how do we take our physics insight and inject it into the neural networks and think of the neural networks as essentially variational models. And machine learning, that goes broadly under the title of inductive bias. That's like not just using some black box function, but using functions that have the right properties. And the basic themes that you see there are ideas like compositionality, symmetry, causality, and scale separation. And you see that already with the convolutional neural network. The idea, part of why these are so successful, is that you're imagining that the features, the images of a sunflower, for instance, if you moved it over, it's still an image of a sunflower. So that somehow there's a translational invariance that's involved, and you can encode that property by using convolutional filters that have shared weights. And similarly, the idea that the world is somehow compositional, that you have like small shapes that make bigger shapes, is implemented through this process called pooling, where you go from the small low-level features to the larger, mid-level or high-level complicated features. And that pooling operation is a lot like renormalization. And so that these ideas are already kind of around, but in most machine learning, for images, it's really just these very basic kind of concepts about translational invariance and this type of hierarchy. And this point was also raised by Stefan Mallat, who's very well known for his work in wavelets and applied mathematics. And he's been studying deep learning and thinking about how they can be used for physics. And he again points to two of the central pillars that's made convolutional neural networks successful. It has to do with symmetries and separating phenomena at different scales. So again, that's very closely related to these ideas that we care about in physics. So I'll say a little bit about some of the work that's been done recently in symmetries, and then I'll say a little bit of the work that's been done in terms of renormalization group and different, going across scales. So I'll have to go quickly here, but so I'll talk a little bit about lattice field theory in particular. So in lattice field theory, you have, you're imagining discretizing space-time into like a four-dimensional lattice. And at every point on the lattice, you're imagining there's some fields, and you might put the data really on the links between those lattice sites. But what the, not the energy, but the Lagrangian for the system is. And so you can calculate the action for any configuration that you're involved with. So this four-dimensional, one instance of this four-dimensional configuration, you can play like a movie where the time direction is being seen as an image. It's being seen as a movie. So this one movie is one sample in this configuration. But what we're interested in is not one of these movies or the dynamics of one of them. We're interested in the statistical properties of this four-dimensional object. So we'd really like to be able to have like many of these four-dimensional configurations, and we would like to sample them according to the Boltzmann factor, essentially e to the minus action. So this is the implementation of the path integral numerically. And typically things like Markov chain Monte Carlo is used to sample this. So what's been done recently is to use what are called flow-based generative models to try to speed up the sampling of these configuration spaces. And it's some kind of hybrid between some machine learning technique and traditional Markov chain Monte Carlo. And so the basic idea here is very simple, is that if you want to model a very complicated distribution, one way of doing it is to start with a very simple distribution, like a Gaussian, and then change variables from what is called z here to phi over here. And if this function is an invertible function, then the density for phi is related to the density in z just through the change of variables formula. So you need to calculate the Jacobian factor for this change of variables, so the idea is that maybe you can use a neural network to implement this change of variables, but if you do so, you're going to need it to be invertible and to have a tractable Jacobian. So one of the ways that that's done is to make a very complicated change of variables. is just to compose a sequence of simple changes of variables. So the composition of many, bijections is itself a bijection, so you can do this. And then there are particular neural network implementations of little, invertible functions that you can compose together. So this idea you can think of maybe as almost like an evolution in time, where these are discrete time steps. And in fact, there's also a continuous time generalization of this, where you start off with, say, a Gaussian distribution and you evolve according to some differential equation to some more complicated distribution. And there's been some work related to the Monge-Ampere flow, which also implements this. And so when you do this, instead of having like layers of a neural network, you actually have continuous time dynamics, and the discrete integration of that system, those time steps, are kind of correspond to the layers of a neural network. But now you actually include an ODE integrator, which might, for instance, be a symplectic integrator or something like that in the mix, which is pretty exciting. And that allows you to model very complicated distributions. So with these kinds of flow-based ideas in mind, the question is, okay, how am I going to train them? And there's essentially two different techniques. One is to train them essentially through maximum likelihood, where you take a bunch of data which you generated through traditional Markov chain Monte Carlo. And that's equivalent to minimizing the Kullback-Leibler divergence between the true target distribution P of X and variational distribution P tilde of theta. So theta are the variational parameters. So you want to minimize this distance, which is 0 when the two distributions are the same. It's also called the relative entropy. The other approach is what's called the reverse KL divergence, where the expectation is taken with respect to the variational model. So you don't need Markov chain Monte Carlo here. What you need to do is propose potential configurations from your variational model, and then you calculate essentially the free energy or the variational free energy, which knows about the true action for the configuration that's been proposed, and you try to minimize this quantity. So this was done, and so what's interesting is that even if the variational model that you learn is not quite right, if it's close, then you can use it actually as a proposal function in the context of Markov chain Monte Carlo, where each proposal is independent. So you don't have a correlation time like you typically do in Markov chain Monte Carlo. This is independence, MCMC. But because both the action and the density for the variational model are tractable, you can correct for any kind of mistakes that are made, and that can lead to producing a Markov chain that exactly samples the target distribution. And so this was done, and what's shown here is that as you change the number of lattice sites, the HMC ensembles, for instance, the autocorrelation time is growing, but in this flow-based approach, the autocorrelation time is basically staying fixed, which means that we're essentially addressing the critical slowing down problem in this problem. And then it's been validated against traditional MCMC approaches, and so this is a pretty interesting direction. Very similar things have been done for trying to study molecular dynamics, where now instead of configurations of a lattice, you're thinking about configurations of a molecule, and you might have, for instance, two very different configurations that are both metastable. And so it's very difficult for a Markov chain to be able to transition from one of these stable states to the other stable state. But in this flow-based approach, you're able to sort of go back and forth between the different states efficiently. And there's a lot of additional related work, which I'll just flash here. So the work that I just showed was for real valued scalar fields. Sorry, complex valued scalar fields, but it says real valued here, but okay, either way, there's scalar fields, but it was not a gauge theory. As if you want to move to a gauge theory, you have several challenges that you need to be able to overcome. So that you have many redundant degrees of freedom that are not really physical, and you also have data that's constrained to some manifold that corresponds to a Lie group. So I'll just be very quick here, but we've been working on this problem, and essentially what we're trying to do is we're thinking about the density of over all the possible configurations, and they're basically gauge invariant physical degrees of freedom where you have some non-trivial distribution. And then you have these non-physical pure gauge degrees of freedom where the distribution should be totally uniform, should be totally flat in those directions because the action is constant. If you use just a kind of generic density estimation technique, it won't know that, and it will be modeling something more complicated, and you'll be very inefficient in trying to learn that, okay, actually this direction is flat and it doesn't matter. So, what you'd like to do is enforce that symmetry directly in the modeling, and that's not so obvious how to do that. And so, I'll just kind of flash some of this work, but first we figured out how to model these normalizing flows on surfaces like tori and sphere that are related to Lie groups. And then we also figured out how to connect that to the space-time symmetries so that we could have both gauge invariance, like a local gauge invariance, and translational symmetry. And I won't go through the details there, but we came up with a procedure where we essentially apply flows to gauge invariant quantities and then propagate them, push those updates onto the links. And it does this in a way that the entire update is gauge invariant or gauge equivariant. And so after doing this, we can look at some examples, and for instance, U1 gauge theory, and you see that as the Markov chain Monte Carlo evolves, that Hamiltonian Monte Carlo basically gets stuck for a long time in different, this is a topological charge in different topological sectors, and it has a very hard time moving from one to the other. The heat bath approach is a little better, but not great. And this flow-based approach you see is sampling the system very efficiently, and the autocorrelation time is orders of magnitude smaller. Okay, since I'm going over so much in time, I'll be very quick here at the end. We've extended this recently to SUN, which was really quite a bit of work to get that to work, and so we are able to model flows essentially on the so-called maximal torus associated to these Lie groups. And so here's an example of modeling not only in SU2 or SU3, but this is modeling a density in SU9 using these gauge equivariant flows on SUN. So that was pretty impressive, and pretty excited about that work. Okay, and there's more work that's going on in this general area of equivariant flows, but I'll just flash it. The last thing that I'll mention has to do with scale separation. And here, the idea is really about the idea of renormalization. So when you talk about renormalization, say if you're coming from condensed matter, the common techniques have to do with real space renormalization group or different types of tensor networks. So for instance, there's this time evolving block decimation tensor network, which is pictured here, which is a common technique to try to model entangled states and things like that. And so what's happened recently is to use the same flow-based architecture that I was just describing. And here it's really just taking two random variables and changing to two other random variables. X1 and X2 goes to X1 prime, X2 prime. So if you have a Gaussian distribution here, you have some non-Gaussian distribution up here, and vice versa. And by taking this block and rearranging it in certain ways, you can input these random variables, at one side, and arranging them this way that's motivated by this particular tensor network, you can have a kind of neural network implementation of the same thing. This kind of approach can be useful in some systems, but it's not appropriate in others because there's a kind of light cone effect in terms of how quickly the correlations grow. But there's also, for instance, the multi-scale entanglement renormalization ansatz, or MIRA. Here's the typical tensor diagram for that. And you can basically implement the same thing again using these normalizing flows, and that's what's pictured here for kind of a one-dimensional system, or you can rearrange them in kind of two-dimensional blocks for instance, a two-dimensional system. And this whole thing is basically an invertible change of variables, but you're inserting noise at various different ways that introduces correlations in a particular way. So these kinds of networks have been used, for instance, to study holography, which is a statement that's saying that if you, for instance, it's related to renormalization, and the idea that if you have a conformal field theory on flat spacetime, you can think of that as being dual to some sort of gravitational theory and a spacetime that's one-dimensional higher. And so it's borne out particularly when the bulk here, this higher dimensional thing, is an anti-de Sitter space, and the conformal field theory lies on the boundary. And that's what the variables here are referring to. And so the renormalization technique is basically starting with the UV theory and sort of decimating the information into the bulk space-time here. And so neural networks have actually been used to try to implement this directly. And the idea, again, is uses these sort of mirror-style networks where information throughout the bulk is introduced, and then it flows through to the boundary. And because you have you can start off with an ansatz like the data in the bulk is all totally uncorrelated. Because you're imagining there's like a massive propagator, so the correlations die off exponentially. And then you can flow that information through this Mira style network to the boundary where you know what the action is. And so you can then try to learn the flow that will give you the correct action on the boundary. And so that's a pretty cool idea. And again, it's trained using this KL divergence, the reverse KL divergence in particular. And that seems like a very interesting direction. There had been some work earlier to try to not think of it so much as a probabilistic way, but to use a neural network to also do this propagation from the field theory on the boundary into the bulk, where the neural network was really evolving the classical equation of motion of some field that would, and there basically how the field should evolve, because if you know what the metric is. And so the neural network is not like some black box neural network. It's really implementing the equations of motion where you're thinking of a discrete time step. And this has recently been generalized to a continuous approach using these neural ordinary differential equations. But here's the work with the discrete time step. And what's cool about this work, I think, is that you can then use it actually in connection to real experimental data where you have some sort of strongly coupled system. So here's a particular material that's being exposed to some magnetic field, and they're looking at the response of the magnetization. And then they relate the magnetization to basically the equations of motion for the field on the boundary. And then through this training procedure, they are basically able to infer what would be the metric, and then they can compare that to, for instance, what you would see in ADS CFT correspondence. Okay, so I lied. I do have one more topic that I was going to mention, which has to do with many-body quantum systems. Here, the situation, the challenge really is that the Hilbert space for a multi-body system grows exponentially with the number of particles in the system, and so you have this enormous exponential growth in the Hilbert space. And so the idea that was introduced was to use a neural network to essentially parameterize the coefficients of all the different possible basis vectors in this exponentially large Hilbert space. And by parameterizing that with a much smaller number of parameters, you have an ansatz that you can work with effectively. And so various approaches have been used here. One is to use something like a convolutional neural network, where the state is the input, and you propagate directly to what you think the wave function should look like. And another approach uses what's called a restricted Boltzmann machine, where you have to sum over what's going on in these hidden layers. Both of them give you essentially, predict what these coefficients should be. And then you can try to minimize, a common goal is to find the ground state energy of these systems. So you minimize the energy by varying the parameters of these variational models. One of the challenges here has been dealing with fermionic states because of the anti-symmetry involved in the wave functions. And there's been recently a collection of different works addressing this problem, and they've shown some very good performance. Here you see the so-called polynet matching the energy, the ground state energy, incredibly accurately compared to an exact calculation that was tractable in this situation. There's some work that I did in this area, which is not trying to find a particular state like the ground state. It's about trying to model the density matrix for a thermal state. And there we use these same kinds of ideas of like maximum likelihood and variational inference, where you use the Kullback-Leibler divergence or the mutual information but we promote those to the quantum versions where we're working with density matrices, so the relative entropy between different density matrices. And we also connected, generalized essentially, instead of using the change of variables formula to change a probability distribution, we were able to modify or flow a complex wave function. And so these ideas, basically extend this sort of analogy that's shown here. I won't sort of go through this in detail, but we did a simple example of using a thermal system for instance, the quantum harmonic oscillator. And we were able to extract the energy eigenstates and the wave functions using machine learning, where we're minimizing this relative entropy, and we've modeled with a neural network type of approach a variational ansatz for the density matrix. And then this is just the sort of working out the details for this quantum version of normalizing flows. So there are many other topics which I don't have time to get into. Sorry, I went over already. There's a number of results using machine learning and really like kind of mathematical physics related to like string theory and various topics like that. So here's a collection of papers. There's also a lot of really, really interesting work which is about using physics to understand the theory of deep learning. And there, people like Linka have been really leading this understanding of using techniques like the cavity method and leaf propagation and the replica trick and things like that to understand the landscape and the dynamics of deep learning. But I won't go into those topics, and instead I'll just conclude by saying that machine learning is really having an enormous impact on physics. It's a very powerful tool for relating experimental data to predictions that are encoded in some very complex simulator, and that's this topic of simulation-based inference. And they also are, very powerful ansatz for variational methods that you see in theoretical physics. And our understanding for how to leverage our prior physics knowledge and while letting machine learning do what it's good at is maturing. And so we're improving in our ability to inject and extract physics knowledge from these models and to be able to exploit symmetries and hierarchical structures in the data. And I invite you to learn more at our workshop, Machine Learning for High Energy Physics on and off the Lattice, which will be held in September 2021. And with that, thank you very much for your time.